in the class today what we will look at is, we will look again at typical orbit velocities, maybe illustrated with some problems, and since you all mentioned something about escape velocities, can we find out what is the velocity required to escape from, let us say, the earth or from some other planet. What is it I am talking of? Let us say, let us come back to the escape velocity first. Let us say I have the earth and I want to escape from this earth as it were. That means I want the force with which the earth is attracting me to vanish, that means I escape. In other words, I am looking at maybe the force is given by g me, maybe the mass of the body which is m divided by r squared, that must go to, that means this force must vanish. In other words, I am looking at, maybe this is radius re, maybe I want to find out the radius at which I can escape from the earth, right, and I have to give the corresponding velocity, and that velocity becomes the escape velocity. Therefore, escape velocity is the velocity required such that I escape from the attractive force of the earth. Therefore, what must be the value of r to escape? I want the force to be 0, I want to escape from the attraction, therefore it becomes infinity, you are right. Therefore, I am looking at r must be infinity in order to have the escape velocity. Now, how do I do this problem? It is the same like what we are doing. Let us say I am looking at the force is equal to m, the mass of the body, mass of the earth divided by r square into g, and what is the work which I must do to take it from here to infinity? The work which I must do is equal to g m me by r square into dr, this is the small amount of work, and now I want to escape from, let us say, the surface of the earth having a radius re, I want to go to infinity, and therefore this must be the type of velocity what I give. And how do I give the velocity? I give the kinetic energy to the body, therefore I give half m into v escape square, and this is what is the escape velocity. And let us find out what this is. We find that mass of the body cancels out, and when I say g me by r square, it is again equal to g me, and here I write re to the value of infinity of dr, I am sorry, this should have been the small increment in radius, divided by r square, and this, if I integrate out, is minus 1 over r, and at infinity I get 0 minus 0, now I get minus of minus 1 over re, and this becomes equal to g me by re. And what is the value I get? This is equal to v escape square divided by 2, or rather I get the escape velocity v is equal to, I get 2 g me by the value of the radius of the earth, which is over here, that is 2 g me by re v to the power under root, and this is the escape velocity. In fact, it is very interesting, we must remember a few things. See, when the earth was born, we had lot of hydrogen which was available around the earth. Hydrogen is a very light gas, and therefore when a light gas is there, as we shall see when we get into theory of rocket propulsion a little later in this class, the velocity at which hydrogen escapes if it is hot is greater than the escape velocity, and that is how we lost hydrogen, whereas on the surface of the earth we do not get hydrogen. The gas goes with such a high speed that it is greater than the escape velocity, and that is how we lost out the hydrogen. Anything which travels at a velocity greater than this keeps on going up and you escape from the surface of the earth. Let us calculate the value. Again we say escape velocity from the surface of the earth is equal to 2 gravitational constant 6.67 0 10 to the power minus 11 Newton meter squared by kilogram square. Mass of the earth 974 10 to the power 24 kg, and with the radius of the earth 6 7 6 3 80 into 10 to the power 3 meters, and this is what is the escape velocity from the surface of the earth. You can just calculate it. Works out to be something like 11.17 kilometers per second. And therefore, if you want to escape, let's say we are talking of a mission to the moon. I will talk about the orbits. Supposing you want to go to the moon, you first go around the earth, you have to escape from the earth, that means I have to have the escape velocity to get out of the earth, then I get into the gravity of the moon, and supposing I want to come back, I need the escape velocity from the moon and come back over here. And this is how we find out the total orbital requirements plus the total velocity requirements to put spacecrafts or any bodies in orbit. This is how we do it. Let me take one or two small examples. We will do one or two small problems such that we are very clear. But however, before doing that, I also want to tell us something about, we were talking in terms of freely falling bodies. What do we mean by freely falling bodies? What do we mean by this freely falling bodies? What did we tell ourselves? I have the sun, I have the 8 planets which are going around the sun, elliptical orbit. We told ourselves all these planets are just falling freely on the surface of the sun, falling towards the sun. But why is it is not falling? Because by the time it falls, it goes through some distance, again it falls, again it goes through some distance, again it falls, again it falls. That means it is just falling towards the center of the sun. Therefore, all planetary motions, all of us are freely falling onto the sun, as it were. And how does a spacecraft now, I say this is the earth, let us for easiness consider something like a circular orbit. If I say this is an orbit, it is going at a constant speed over here, it falls towards the center of the earth, again it goes, because I give an orbital velocity, it goes like this, but again it falls. Therefore, all the bodies which are in orbit are something which we call as freely falling bodies. It is as good as I drop a stone and it falls freely, so also all the bodies which are in orbit are freely falling. And what is the function, or what is the thing which we understand by freely falling bodies? Let's take 2 examples. Let us assume I have a stone, it falls freely, but let us assume that there is no resistance due to air, because we are talking of space, therefore it is just falling freely. I also take an example of an elevator or a lift. We climb to this room through the elevator, and let us say the elevator falls freely. Let us take an example. I am in the elevator, maybe this is the elevator which is falling freely. I am going down, it just falls freely. Maybe I am standing over here, and in my hand I hold a cup of tea. You all would have seen this. Now, what happens to the teacup when I am holding? See, what is it? This stone is freely falling, this is freely falling, this is not an inertial frame of reference because it is picking up acceleration. Therefore, it is something like a linearly accelerating frame of reference. It is different from the rotational frame of reference. I am just taking this body. Now, my point is, supposing I am standing over here on the stone, or I am sitting or I am standing in the lift and I am having a teacup in my hand. Now, what is the force which I will experience on this teacup? Can somebody tell me? All what I am talking is, yes, I have, maybe the earth is over here, earth is attracting me, and therefore I have to correct, because it is not a initial not an inertial frame of reference, I have to put some corrective force over here, and therefore what I have to put is, maybe the stone is freely falling, I have to put some force here, because for me I am not moving at all, therefore I have to put a pseudo force opposite to the attractive force of the earth. Attractive force of the earth is G me m by r square, and I have to put a pseudo force here which is equal to this, and the moment I put a pseudo force over here, my motion is taken care of. I am able to describe my motion correctly, because I am not moving with respect to the stone, I am not moving with respect to this lift, but when I put a force equal and opposite to the force with which I am attracting, the net force on me becomes 0, and when the net force on me becomes 0, I am weightless, I am in a state of, how would I take a look, I am in a state of weightlessness. Why is it I am not having any weight? It is not that I have my weight, but to be able to correctly define me, because I am dropping along, I am sitting on the stone is coming down, but I have to correct my motion, because I am not moving with respect to the frame of reference of this stone, because I am not moving, therefore I have to put a pseudo force vertical to it, and I am now attracted by gravity, but I put the force equal and opposite to the gravity, then only I can say I am not moving. Therefore the moment I put the pseudo force, I do not have any force or weight, I am in a state of weightlessness. Some people call it as 0g. Actually it is not 0g, g is gravitation. Gravitation is always there, but a body in orbit, which is also a freely falling body, is always in a state of weightlessness. That means a freely falling body is in a state of weightlessness. It does not have any, it is not able to see any weight, and so also if in this lift itself, suppose I hold a teacup and come down, you will feel it is not heavy at all, it is as if it is 0g, because I have to, I am standing here, I have to correct my motion using a pseudo force, and that is why whenever you see the pictures of maybe astronauts in space, you say they are all floating around, there is nothing to really hold them, because you have to correct their motion by a pseudo force, and you see whenever you see the astronauts in a space capsule, well, they are just floating. And to be able to drink a cup of water, supposing I go there in a deep mission, I am very thirsty, it is not possible for me to drink water from a cup, because it does not settle to the bottom of the maybe tumbler or the cup, therefore it will be freely floating. That means I have water in a tumbler, but it will just be floating. Therefore what one has to do, maybe one has to arrest it somewhere, maybe put a straw, suck it through, then only even drinking little bit of water in space when I am orbiting becomes a problem. This is what we call as a state of weightlessness, or we call it as, some people call it as 0g, but let us not confuse, g is always there. In fact, since many of you are from mechanical engineering and working in combustion, if you have, let us say, a candle, flame is like this. There are some experiments done in orbit, what does the flame look, and how will a flame look in space? Why do you have this shape on ground, and how will it look when the same candle you strike in orbit, in an orbiting spacecraft? How should it look like? Any guess? And this is very powerful. What is happening? The gas becomes lighter, buoyancy force, and that is how you have this. The lighter gas rises and you have the candle flame like this. If I were to look at it at spacecraft, I have the candle again, it will be pure sphere, because there is no weightlessness, it does not have any lightweight or strong weight, it is just a perfect sphere, and that is where my equations which I described, I can have a spherical frame of reference, I can solve for the diffusion equation, and I can solve for the energy release equation, and I am able to find out what is the mechanism of a diffusion flame much more strongly than if I can do a experiment on the ground with a candle. And in fact maybe little bit later on I will bring some pictures and show how maybe an astronaut drinks water in space, maybe how does a plant, how does a flower which is growing in space, how will it look, how it will be different, and there are pictures which are available on this. Therefore, what is it we have done so far? Let us quickly summarize and do one or two small problems which will make sure that we have understood the subject. We talked in terms of orbiting of the different planets in our solar system. We went ahead, we formulated the universal law for gravitation as determined by Newton. We told ourselves, well, all planets are falling, an apple is falling, and he said a heavier body attracts a lighter body, and you have the universal gravitational law. We used the gravitational law and we found out V0 is equal to g me by r, where r is the orbit and v is the orbital velocity. We also found out that the total velocity required to orbit for a circular orbit is equal to g me by re into re plus 2h divided by re plus h under root. We also talked of geosynchronous orbit, polar orbit. Maybe we told ourselves for remote sensing we go around so that I can see the entire earth as it were. For communication, TV and weather predictions, maybe geosynchronous is better suited. I can also have low earth orbit around the earth at different altitudes and all that, and we found out the total velocity requirements. We also talked in terms of the escape velocity. We said it is equal to 2g me by the radius of the earth from the surface of the earth. If I have something which is orbiting at a distance r from the surface of the earth and I want to push it to infinity, then in this case it becomes r, right. And this is all what we have done so far. Let us take one or two small problems, but before doing the problems I will quickly revise what we have done so far, and let's take a look at this PowerPoint presentation. See here we see the a low earth orbit going around the earth as it were. This shows the sun's geostationary orbit. You have the earth as it were, this is the east to west, and you find that the spacecraft is going round at a height of 42,164 kilometers. It is in the equatorial plane. This is the earth and this is the radius what is there. You subtract the radius of the earth and that is the height of the geostationary orbit. Geostationary. This shows the earth equatorial plane going round east to west, and supposing we have an orbit, let us say I have the earth here, I am sorry it should have been a circle. Instead of going from east to west, I go from west to east. I am going against the rotation of the earth, and such orbits are known as retrograde orbits. Retro. But those are nowhere used, because why should I go against and not get any benefit at all. Let us go to the next one. This shows the first SYNCOM-2, the first geostationary satellite which was launched by US was not successful, therefore the second one was successful. This was on 26 July 1963 and it relayed the Tokyo Olympics. This is a polar orbit, you go from north to south, you see this is the north to south, you are going around it like this, and you also find that this angle is not really 90 but a little more than 90. This shows the highly elliptical orbits, this is the perigee, this is the apogee, this distance we said for Molniya orbit is something like 42,000, this distance here is of the order of 6,000 and this is an elliptic orbit. And now few other orbits, since we talked of orbits, supposing I want to launch a satellite into geostationary orbit, I first take off from the ground, I put it in an elliptic orbit, I put the apogee equal to something like 42,164 highly elliptical orbit, and when it comes to the apogee I make sure I fire a rocket and make sure it goes along this and I get a geostationary orbit. Suppose I am talking in terms of a moon mission, Well, Chandrayaan 1 of ISRO, well, it is from the earth, I keep going like this, I escape from the earth, I get inserted onto the moon. If I want to come back from the moon, I again come out of the moon gravity, I escape from this and I have to come back. These are the different orbits. Therefore, in the previous slide I had something known as a transfer orbit. That means I am not talking in terms of a geostationary orbit, but to be able to go to this, I first put my object in a transfer orbit and then when it is at the apogee I circularize it. Well, these are the different orbits and it is time for us to do a problem, and I take a problem which is something related to a recent rocket. You know, we have a person, I'll just tell you about it. You know, a person by name Sir Richard Branson. Because I thought let us do a problem which has some practical relevance. Sir he is a commercial person, he wants to take tourists from the surface of the earth into deep space. You know, people would like to go to the above the earth and see the earth as it were, how it looks, and it seems to be very fascinating. Therefore, what he proposes is, he talks in terms of, and that is what I show in this transparency, he talks in terms of an aircraft. This aircraft is known as White Knight 2. It is a little stronger aircraft. You have engines here, you have and it carries a rocket and a space capsule, and what it does is, the aircraft takes off from the surface of the earth, goes to a height of something like 15 kilometers and it returns. At 15 kilometers you fire a rocket and it takes you to a distance of something like 100 kilometers. Therefore, I want to find a problem wherein maybe from 15 kilometers above the surface of the earth to 100 kilometers where a rocket takes you, what is the value of velocity to be provided by the rocket. Because if I say the velocity required from the surface of the earth to 100 kilometers I know, but now it takes me from 15 kilometers to a distance of 100 kilometers. That means I am looking at this, up to 15 kilometers the aircraft is taking me, White Knight 2, and from here to a height of maybe 100 kilometers the rocket is taking me. I want to know what is the velocity which must be provided by the rocket. How do I do this problem? Let's calculate it. You know, we say velocity half m into the velocity half m into v square is the velocity, is the net kinetic energy what we are giving. This must be equal to, I start from 5 kilometers above the surface of the earth, that means RE plus 5 kilometers, I go to the radius of the earth plus 100 kilometers, and what I do, I give this kinetic energy which will give me the work done, and what is the work done? G me m by r square in a small distance dr, this is the work. Therefore, as I go from this to this is equal to this. And now how do I get this? I have to solve this equation and find out what is the value of v. How do? I find m and m gets cancelled, G me by r square gives me minus 1 over r, therefore I get 1 over, let's do this, v square by 2 is therefore equal to G me, m goes out, I have something like 1 over radius of the earth, we were telling it is equal to, we just take this value kilometers, therefore RE plus 5 kilometers is 6383 minus 1 over 100, that is 6483. We substitute the value of G 6.670 10 to the power minus 11, the mass of the earth, and I get the velocity what is required, and this velocity will come out to be something like 1.278 kilometers per second. and once you know what is the velocity which must be given, I can design my rocket accordingly, and that is what I will be doing towards the end of this class today. Therefore, you find now this question is, had I started from the surface of the earth, which is we say 6378, I find that the difference in velocity is going to be very small. Therefore, I really do not see any advantage in launching from an aeroplane and going up. But something which we are forgetting, an aircraft when it goes like this, it also gives you a horizontal component, namely an orbital velocity component, and that is what makes it advantageous. We have some rockets, and one of the rockets, please take it down, it is known as Pegasus Rocket, and in this rocket what is done is, you take the rocket and the spacecraft in an aircraft to a height of something like 10 to 15 kilometers where atmosphere is available, you launch the rocket, and that way the rocket need not be very powerful, but it can be a small rocket, can do the job. Therefore, we call these things as air launch. We will do some more examples and we will be very clear about it. Therefore, a rocket need not always be launched from the ground, it can also be launched from under the sea. We have sea launch, we have something known as a Polaris Missile, which is launched from a submarine, maybe from under the water, it comes up and it can go. Therefore, wherever we want, all what we want is, we need the value of this to this, and we can find out the velocity what is required. This is all what we learn in orbital velocities. Maybe I will take a next example which is very illustrative. I told you that we talk in terms of geostationary orbits, right, and nowadays we find many countries are wanting to launch spacecrafts into geostationary orbit, because this is very useful. I just go and maybe point it towards Nagpur, which is the center of India. The India gets covered. Whenever I want a TV, I just switch it on. I beam the program to the satellite and it beams it throughout the country as it were. Therefore, is there any problem? Is there something like life of a satellite? Let us say INSAT. Some INSATs have been launched as early as maybe in the 1980s and all that. Is there any problem? Can it keep on going continuously, or is there a life? And if there is a life to a satellite, why should it have a life? Because electronics can continue to function for hundreds of years. Therefore, why should there be a life? What is your thinking? Any thinking on this? Because people keep telling this satellite is launched only, it has a lifetime of 15 years. Some say it has 20 years, some say it is only 5 years. What decides the lifetime of a satellite? Because I keep telling everything is freely falling, everything is vacuum, everything is going around. If there is so what, why should there be something like a life of a geostationary satellite or life of a spacecraft? Why should it be there?
So if the satellite is deviating from the path, we give some small thrust.
Yeah, you are telling maybe the satellite may be deviating from its path. Why should it deviate? You are right, but why should it deviate is the question.
Any unknown forces are there?
Yes, there are many other forces, like for instance you have the sun, you have solar flares, the gravity of the sun is changing. Maybe you have the moon somewhere, we are already something like at a height of something like 43,000 kilometers. There is moon's attraction, that is also variable. Therefore, it is quite possible that there are perturbations or changes. And how do you take care of these perturbations? You have to supply some, you will have something like, if you have INSAT spacecraft, something like a box, let us say, you have something like 16 rockets put at all the corners, and whenever you find something is changing, I have to fire these rockets and maybe make it point, alright. That means I have to do something like what we call as station keeping. I have to keep on, make sure it is always pointed here. If it drifts, I have to correct it. That means the attitude may change, attitude means I am talking of the position, the orbit can change. Therefore, I have something like for attitude and orbit some corrections are required. Therefore, for all these things I fire rockets, and therefore I have to take a fuel tank and I use it, and once my fuel is over, the life of the spacecraft is over, and that is the problem with these spacecrafts. And that is why we keep talking in terms of exotic propulsion like electrical propulsion, which may not have so much requirement of a fuel, which can be there for much longer time, and therefore we will cover these things as we go along. But the point I am trying to say is, supposing we have something like a geostationary orbit, and we told ourselves the geostationary orbit is over here at a large height, something like 43,000 from the surface, and let us say some of the spacecrafts, some of the geostationary spacecraft is the life period is over. If it is going to be there, maybe the next spacecraft may collide with this. That means I have the old non-functional spacecraft, and therefore it may collide and it might be a hazard for me. That means there is a problem even in space, even though the space is so much, I keep sending another satellite, it may collide with this, and therefore my new spacecraft may not function. Therefore, it is necessary for me to be, once the lifetime is over, to push it out with escape velocity such that it goes into deep space and I have no such problem. How do I do it? In other words, before the INSAT satellite the life is over, I should make sure that with the remaining fuel I must push it out such that this orbit, which is geostationary orbit, is available for me. Therefore, let us do that problem. I deliberately chose this problem. All what I am saying is, I have a geostationary satellite, and now I want to push it out of the orbit. That means I have to push it to infinity. That means it goes off. Therefore, I am not really bothered. Therefore, what is the velocity required to push a spacecraft out of the geostationary orbit into deep space? That means I have to escape from the earth. Let us forget about the pull of the moon, other planets and all that. Let us assume only earth is attracting. Therefore, I want to find out what is the escape velocity. Escape velocity is equal to 2 g me by r. What is r now? I want to escape from this orbit, and what is that r? R is equal to what we said was something like 42,000 kilometers. I put the value of r, I put the value of g and me, and I find that I still require to push it out something like 4.347 kilometers per second. And how? Let us put the numbers here, is equal to 2 into 6.670 10 to the power minus 11 into mass of the earth 5.974 10 to the power 24 divided by, you have r, which is equal to 42,178 into 10 to the power 3 meters, and this comes out to be 4 point. That means, even when I have a geostationary satellite, I must keep some fuel reserve such that with that fuel I will be able to push it out, and these are all mandatory. Well, this is all about orbits. I think we have covered it in some extent. And why do we need rockets? We will again go back and ask ourselves, what did the others do? We told ourselves, well, Jules Verne in his book From Earth to Moon, what he said is, you have a cannon. In the cannon you put something like a spacecraft, you push it out with extremely high velocities such that it gets into orbit. What is the type of typical orbital velocities for a geostationary orbit? Is around 13 kilometers per second, or let us say, we say maybe I need an orbital velocity, or the total velocity required is around let us say 10 kilometers per second, that is 10,000 meters per second. Supposing the mass of my body which I want to orbit is around, we say 1000 kg, because 1000 kg is something wherein I can put some equipments, maybe 1 or 2 people can be there, you have something for life support and all that. 1000 kg seems reasonable. Therefore, what is the energy I must have? I talk in energy into 1000 kg, kinetic energy 10,000 square and so much joules is the energy what I have to give, maybe kinetic energy I have to give. And what is this value? Supposing I have to launch it instantaneously, let us say I launch it in something like 0.1 millisecond or let us say 1 millisecond, because it has to go fast, therefore the power required is equal to half into 1000 into 10,000 square divided by 10 to the power minus 3, and what is the number we are talking of? We are talking of 500, 5 into 10 to the power 5, 10 to the power 5, and I have, we are talking of 4 zeros, 10 to the power 8, we are talking of a huge number, something like 10 to the power, let us say 8, 7, 8, 8 plus 3 11, 11 plus 3 14, that means something like 10 to the power 13, 5 into 10 to the power 13, we are talking of a number of this order of so much watts. If you take the entire electricity which is generated in a super thermal power plant, it is very much lower than this. Therefore, we cannot use a launch like this. And if we take a look at what we were telling, somebody imagine maybe a ship is sailing on the sea, there is a giant storm and you get a high velocity. Even if by chance I get a high velocity, when the body with a high velocity is traveling through atmosphere, it will get burnt out, right, because you have frictional resistance of the air. Therefore, we need some other type of objects, and when we say rocket propulsion, all what we mean is you have a continuous ejection of mass at high velocities. What it does is it provides us some momentum, or rather some change of momentum. And what do we mean by change of momentum? We call it as impulse I. What is the unit of a momentum? Momentum is kilogram meter per second, therefore impulse has the same unit, kilogram meter per second, but Newton is equal to kilogram meter per second square, therefore impulse also has units of Newton second. Please be careful about units. Therefore, all what we are saying is we must give some impulse to the body by depleting the body of its mass, starts slowly, keeps rising up, and that is what is the theory of rocket propulsion, and that is what I will consider now. Maybe we will take an example, we will illustrate it, and in the next class we will go ahead. This brings us to the theory of rocket propulsion. All what we are telling is I must give some momentum to the body, and how do I give momentum? I throw some mass out of the body. Therefore, let us take an example. We will start with this example, it is a very fascinating example, and what I do is I borrow this example from my teacher. What he used to teach the mechanics students, and one of the problems he used to give is, supposing we have something like a sled. What is a sled? Sled is something which maybe you go on a mountain slope and all that, you attach yourself and you go down the slope, that we call as a sled. And in this sled, let us say we are in a place where there is no attraction due to gravity, no external forces. On this sled maybe we have two boys who are standing in this sled. The sled is stationary and these two boys want to move the sled. The sled is on a ground, let us say the ground is so slippery that there is no friction, let us say there is no gravitational force and all that, we idealize the situation. The sled is stationary, these two boys find hey, it is all ice here, that means there is no friction, they do not want to get out, they want to move the sled. Therefore, they say let us provide some impulse, or let us provide some momentum. Therefore, we take an example where each of the boys has a mass m of stone, they both carry a stone of mass m over here. Let the mass of the stones, the two boys and the sled be capital M kg. Let the mass of each stone be told is small m kg. Now the boys want to move, and how do they move? They say let both of us throw this mass out at a velocity v0. so much meters per second. Therefore, both the boys simultaneously throw this mass with a velocity v0 meters per second. Now I want to find out whether this sled will move or not. How do I solve it? I go back to my inertial frame of reference. What I do is I stand over here and I am in an inertial frame of reference because I am moving at constant velocity and therefore I can describe the motion of the body. I am watching these things happen. Now I want to know at what will be the velocity at which the sled moves. The two boys throw the stone in this direction with the velocity v0. Let me assume that the sled also moves in the same direction at a velocity v meters per second. I want to determine the value of v. I am looking at it from the inertial frame of reference and therefore what will be my equation? The initial momentum of the sled, the boys, the stones put together, they are all at rest, v is equal to 0 initially, and therefore the value of velocity, initial velocity is 0. Therefore the initial momentum is 0, right. What is the final momentum? The momentum is conserved in the inertial frame of reference. Therefore what is the final momentum? Let us calculate it. Now the final mass of the sled is m, 2m of the mass of the stones has left. Therefore the final mass of the sled is equal to m minus 2m. Let us assume the sled has a velocity capital V, v. Anything else? The stones are leaving the sled. Now what is the velocity of the stone? I am watching it from the inertial frame of reference. The sled is moving with a velocity v, stones are moving with a velocity v0, and therefore I get 2m into v0 plus v in the initial frame of reference. Momentum is conserved. Initially it is 0, final must be equal to this, because I am talking of the inertial frame of reference, and therefore this frame of reference is very important in any mechanics problem. Let us be very clear. Now I want to solve this, therefore I say initial momentum is 0, this is equal to mv minus 2mv plus 2m into v0 plus 2m into v, this and this gets cancelled, I get v0 is equal to, or I want to find out the final velocity of the sled, I am more interested in capital V is equal to, what is the value I get? V is equal to minus, yes, what is the value? 2m divided by m into the velocity with which the stones are thrown out. What does this equation tell us? If the stones are thrown out in this direction, the velocity will be in the opposite direction. So far so good. Therefore just the action of these two boys throwing a stone, they are able to move the sled at this velocity, right. Now I ask the second question, yes I have this, what is the relative velocity? V plus v0, that is v plus v0, that means I say that the value of v plus v0 velocity is equal to, now I say v plus v0, therefore I get v0 outside into 1 minus 2m by m into v0. I am sorry, I have already written v0 here. That is the relative velocity of the stone with respect to the motion of the sled. Now let's spend some time on this, we must understand it, and I will just extrapolate this and get you the rocket equation or the theory of rocket propulsion. Does it make sense? Let's go forward. We will ask ourselves the next question we ask ourselves is, well these two boys, they are wise, they know precisely what they want the sled to move faster. Therefore they say, yes I have this boy first throws the stone and the same stone of mass m, then after some time the second boy now throws the second stone. In fact they do not throw the stones simultaneously, that is 2m mass of stones thrown together, but rather one stone after the other. If the stones are thrown one after the other, what will be the final velocity of the sled? I call it as v prime. What should be the value? Let us write the equation of motion again. I am in the inertial frame of reference, I stand over here, watch the fun in the inertial frame of reference. I find that the first boy throws the stone, and therefore the value of V prime, that is after the first stone is thrown, I call it as V prime, and that will be equal to minus, only one stone has been thrown, it is equal to capital M into V0, right, because only one stone is thrown. And what is the relative velocity? The relative velocity is equal to V plus V0, that is V prime plus V0 is equal to V0 into 1 minus small m by capital M. At this point in time, the second boy throws the stone, and therefore what is it he is getting? Now he is getting, when the first stone is thrown you have V prime, when after the second thrown is thrown you get V2 prime. Let us balance the momentum. I am in the inertial frame of reference, I want to balance the momentum change, and therefore what is my momentum equation? Initially they are at rest, when the first stone is thrown you have the velocity is given by the initial velocity is there, the final velocity is again the same thing, m minus 2m into V2 prime. The first stone goes with a velocity of relative velocity over here, which is equal to m into V0 into 1 minus m over m, and the second stone goes with a velocity m into the velocity is equal to V2 prime plus V0, relative velocity, final is V2 prime, the velocity of the stone, therefore this becomes my final equation. If I solve this, what do I get? Let us solve it. I want to find out what is the final velocity. I find I have mv2 prime, 2mv2 prime, mv2 prime, I take it inside, I get is equal to, or I get 0 is equal to m minus m into v2 prime plus I have mv0 into 1 minus m over m, I have mv0, I keep it over there, 1 minus, or I get m minus m divided by capital M, and I have mv0. What do I get? What do I solve? I want to solve for v2 prime is equal to, now I get m over capital M minus small m into v0 plus I have m divided by m into v0, or rather I get v0 into small m by capital M plus I get small m by m minus m. Is it all right? Now let us take a look. When one stone is thrown after the other, I get this velocity. When both the stones are thrown together, we had something like 2m over m over v0. Which is more? Which is, again, mind you, here also I should have had the negative sign because it is opposite, and therefore what is the comparison? Here you have m over m plus m over m, here I have m over m plus m over m minus m. This is smaller, therefore this will be greater, and therefore the art of throwing one stone after the other gives me a higher velocity to this. Now I can generalize it. Instead of having two stones, I keep on throwing one stone after the other. What is going to happen? I will get the velocity which is much better than the spontaneous throwing of all the stones together, and this is the basis of the rocket propulsion. What we do is, I have a rocket, I put, let us say, lot of stones in it, I keep throwing one stone after the other, keep on ejecting mass, and that is how I get a final velocity. I will continue with this. In the next class we will derive the Tsiolkovsky equation, which is known as the rocket equation, just following this analog. I will again extend this to more number of stones and do this, but this is basically the principle, and if this principle is clear, we must be able to design new forms of rockets, and that is why I cover this. Well, thank you then.